I hope you had a safe and restful break. My goal today is just to do a review of what we've talked about so far, mostly with concepts, but at the end of the day, there's going to be one practice problem that we're going to do. But we're going to do most of this on Socrative. And then we won't have a daily assignment like we've had previous days. So that's my plan today. We got one more thing that I'm going to teach you on Thursday. My plan when you, assuming that you are back here on Monday, which it seems like it's going to be, I will give everyone a chance to, we'll essentially do some practice problems together while I'm there to answer any questions that you got, and we will move on from there. I'm looking at final exam. I'm looking at a test the second to last period before the end of school. So if you're planning ahead, maybe that'll help you. All right, here's what I'd like you to do. We're gonna log into Socrative. Let me give you the link here. So in the chat, I'm putting the link for you to go to. And then the code that you need to enter is RORFIZ. That's that. So again, if there were a couple people who just signed on, I'll put it again in the chat in case you didn't get it. There's a link you need to go to, and you're going to enter in that code. And once you're in, there's a question that you can read and get started on. But again, go to that website for Socrative, use that code, and then you can enter your answer when you think you're ready, and then we will go from there. So it looks to me, if I missed you, please speak up, but it looks to me like currently I'm missing both Landons, Nick, Brady, Eros, Ethan. Did I miss any of you? Are there any of you hiding in there? All right. Hi, Landon. I'm putting in the chat right now. There's a website we're going to, and then we're making this code. Again, so everyone, so the question, if you haven't yet, it looks like we got about half of people who've answered it so far. Just your best guess here. When an object is spinning in a circle, why does it feel like it's moving outwards, even though the centripetal force always points inwards? No luck, Dalton. Is it, does the link give you a way to type the code, or does the link not even work? It's the code that I put in there. Yeah, what Haley just put in. Yeah. All right, so I'll go ahead and show the results for this first one. Good, it's the object's inertia that makes it want to continue moving in a straight line. There is no force, remember, there is no force that pushes out. I'm going to go briefly to my document camera for a second. So remember, this was the first day of notes. We took these notes on uniform circular motion, and we said you have to have forward motion, which is maintained by inertia, and you have to have centripetal force. You have to have both things. But there is nothing pushing this out. The reason things appear to go out is because their inertia, pardon me, makes them want to go in a straight line. And then that bucket, whatever that object is, it just kind of gets in the way. The centripetal force prevents it from doing that. But there is nothing pushing it out. All right, let's go ahead and try the next question here. All right, I don't know if you've ever played tetherball before, but in tetherball, there's a ball tied to the top of a pole like this, and the idea is you're trying to hit it around the pole. The goal is to like get it all the way around. But just when I'm hitting this around and it's going in a circle, you've got this rope here, and you've got gravity. So my question is, what is providing the centripetal force in this case? All right, let's see what we got here. So Brady, real quick, I'm putting in the link to where you need to log in one more time. But let's see what we got. Along the horizontal, so we got half of us say along the horizontal component of the tension force, and half of us or part of us are saying tangential to the circle, and we've got a few other answers here. I want to pull up PowerPoint that I made here.
Is room name the code?
Correct. Yeah, the room name. So taking a look at this picture, I kind of want to draw the free body diagram. Remember, the point of a centripetal force is a centripetal force has to point towards the center. So what we've got here is you have to imagine this centripetal force is doing two things, right? And it's got two components. Call it the y component and the x component. So the deal here is, right, the point of the y component is it cancels out gravity. And what you're actually going to see is that the centripetal force that's pointing towards the center has to be coming from the FTX. So if I were to actually solve out this problem, what I'd do is I'd say centripetal force is mass times centripetal acceleration. And the centripetal force in this case is going to be equal to the horizontal component. So that would be how I solve this. So the answer should be that what's providing the centripetal force is the horizontal component of the tension. All right, let's see what we can do with this next one. You're a passenger in a car not wearing a seatbelt. The car makes a sharp left turn. From your perspective, what do you feel like is happening to you? Hey, let's see here. Would somebody do me a favor and make a copy of the last thing I put? I don't have a very good way to get to my chat and tablet mode. A copy of the last thing that I put in for Ethan. Thank you, Aiden and Kevin. Appreciate it. So Ethan, what Kevin and Aiden just put in, if you just click that link, and then that's the code you need to log in. Okay, good. So we have this experience, right? If you turn left, you feel like you're thrown to the right. Okay, so that makes sense. Now, my question is, which of these examples explain what's actually happening? Oops. Where'd it go? All right, let's see what we got. All right. So this is one that's interesting to think about, right? Now, you probably were able to answer, if this wasn't a multiple choice question, you probably would have said something about inertia. But I want to explain why it's that the door is exerting a leftward force on you. So let's see here. So here, what I've kind of drawn here, right, is a car that's turning, right? It's a car at several different points in time. So imagine that you're here in the passenger seat, right? Well, come on now. I'm having. My pen's out of battery. Just 1 second here. All right. So if you imagine that you're sitting here in the passenger seat of the car, right? The idea is you want to keep moving forward, but what happens a moment later, the car is now in your way. So it puts a force this way, right? And then now what do you want to do? Now you want to keep going in a straight line this way. But a moment later, the car is in your way. And what's going to happen? It's going to put a force this way, right? And so what's happening the whole time is the only real force you have is a leftward force. We might call that a normal force in this case, right? There's a leftward force coming from the door that's pushing you inside. There is nothing pushing you out. I want to point out there are two terms that are closely related. You may have heard about this thing called a centrifugal force. So there's this thing that you may have heard of before, and then there's the one we've talked about called the centripetal force. Now, it's important, so when we think of centrifugal force, this idea of fugal, so fugal comes from the same root word that like fugitive does. So a fugitive is somebody who's fleeing from law enforcement or whatever. So that root word means it's a center fleeing force. This does not exist. There's centrifugal force is what's called a fictitious force. It does not exist. There is no center fleeing force, anything that pushes you out. It's an illusion. What does exist is a centripetal force. A centripetal force points toward the center instead of away from the center. So you always have a force pulling you towards the center when you're going in a circle, but you do not have a force pushing you out. It's just it's an apparent, it's just the effect of your inertia that makes you seem like you're being pushed out, but in reality you're being pulled in, and it's inertia that makes you want to keep going in a straight line. All right, any questions so far? All right, let's go to the next question. You are on a Ferris wheel moving in a vertical circle. When the Ferris wheel is at rest and you're sitting on it, on your chair, right? The normal force exerted by your seat is equal to your weight. How does the normal force change at the top of the Ferris wheel when you are in motion? So while I'm going around in a circle, is the normal force at the top of the Ferris wheel larger, smaller, or equal to gravity? Oh, Eris, here, what you need to do is, actually, can someone else do it for me again? There's a link you need to go to. So if somebody else could just copy, thank you, Aiden. So that link that Aiden just sent, go to that link and log in with that code, and that's how you can enter your answer. All right, let's see what we got. All right. So let's think about what's going on here. So remember, the thing that you have to have at all, whenever you're going in a circle, you have to have a centripetal force, which is a force that points towards the center, right? So let's think about what's happening when you're up here at the top. When you're sitting on your chair up here at the top, right? Let's think about what forces are acting on you. You've got gravity that's pulling you down, and you've got normal that's pulling you up. But the thing is here, right, we need, let me actually draw this a little bit better so it's clear what we need, right? When I'm right here, gravity is what's pulling me towards the center, right? I need my centripetal force in the end to pull towards the center. So in order for my centripetal force, my net force to point towards the center, my normal has to be smaller than gravity, because the one that's pointing towards the center has to win, right? So in this case, the normal force has to be smaller than gravity. When I'm at the bottom, I didn't ask you this, but the situation is the opposite at the bottom, right? Because at the bottom, gravity is pulling you away from normal. So if you want to have a centripetal force that points towards the center, now at the bottom, you have to have a normal force that's bigger than gravity. So at the top, you need gravity to win because gravity points towards the center. At the bottom, you need normal to win because normal is the one pointing towards the center. All right. Next question. So this is a similar, but now I'm asking you to calculate what the net force is, or which of these is correct about the net force. So you've got a skier here trying to ski over this hill that we're going to imagine is a piece of a circle that has a radius. So what is true about the centripetal force in this case? Is it equal to normal plus gravity, gravity minus normal, normal gravity? Which of these is it equal to? All right, very good. Very good. So we're thinking very similar to how we were thinking last time, right? So again, the force that goes towards the center, which would be gravity, has to be smaller or has to be bigger than the force that's pointing against it, because I want my centripetal force to point towards the center, which is down. So in this case, centripetal force would be equal to gravity minus normal. All right. One more multiple choice question and then a few other thinking questions. Oops, I hope you didn't see that. You swing a ball at the end of a string in a vertical circle. Since the ball is in circular motion, what is at the very top, what is the centripetal force equal to? All right, good. Now, this is one, you guys did not fall into the trap, so that's good. I want to be clear about, because when we're talking about normal force, right, a normal force pushes, a tension force, however, pulls. So when you're doing this one, right, so this is the ball at the top. When you're doing this one, if this were a normal force, it would go that way. But this isn't a normal force, it's a tension force. Tension forces pull. So the tension force will go this way. Obviously, you've got gravity that is also pulling. So in this case, the centripetal force would be tension plus gravity. All right. Before I go to the next question, I want to share a video real quick. Share. Let's go to this one here. I don't know if you've ever ridden one of these rides. Yeah, Graviton, Russell. That's 2012. I don't know what that is. So anyway, if you've ever, if you've ever ridden one of these, oh, I don't know, I just found it somewhere, Russell. But the idea is you're in this big room that's spinning, and you're not supposed to actually stand up like this guy did, but you do feel like you're being pushed against the wall. Again, we know there's no force that's actually pushing you against the wall. It's because of your inertia. But what I want to do is I want to think about what the free body diagram for this would look like. You banged your head on the wall like you were, you like weren't sitting with your back against the wall. Let me see here. If I get back to my Socrative. So what I'd like to do here is, yeah, I think that what that guy, I don't recommend doing what that guy did. And as a matter of fact, I doubt that they actually, I'll bet that's frowned upon. But here's what I want you to think about. I want you to think about, so that, the video that I just showed you, right, the walls were kind of slanted. Just to simplify this a little bit, let's assume that the walls are exactly straight up and down. And my question is, which of these, there are 5 free body diagrams here, which of these do you think is correct? And then I'm going to ask you to go a step further. Which free body diagram do you think is correct? And then can you label the forces, right? So what are the forces on the diagram? Are they gravity, normal, tension, friction, etc., right? So tell me which of those you think is the correct free body diagram, and then you give your best guess about how you would label the forces that are drawn on there. There's a black, can you not see the free body diagrams, the 1, 2, 3, 4, 5? Aiden, I think the black square is my chat. I can see them. Okay, yeah, that's what's important. I think the black square is my chat where I'm talking to you. No, that's fine, Kevin. So which of those free body diagrams 1 through 5 do you think it is? And what are the forces? Are they gravity? Are they friction? Are they tension? Are they normal? Right? So like, for example, if you picked 3, you would tell me, what do you think the downward force is? And what do you think that the leftward force is? Cool. That's all right, Russell. I just want to see what people are saying about this. I got 5 applied force to the right, friction, centripetal gravity. So actually, I have not yet in any class had anyone get this perfectly right until now. I've got one person here that I think has it pretty close. Is there a way to go back? I don't know that there's a way to go back, Russell. You don't have to worry about it. This is actually almost exactly right. This answer here is almost exactly right. So again, there is no outward force. There's nothing that pushes you back. It's your inertia makes you feel like you're being pushed back, but there is nothing actually pushing you back. Let me go back to my PowerPoint here. Right, so this is the correct, this was number 1. This is the correct free body diagram, right? And if we label these, right, it's pretty obvious the downward one is gravity. The other 2 are a little bit weird though. We're used to normal being the upward force. However, remember what the term normal means. Normal just means perpendicular to the surface. So in this case, if you've got your surface here going vertically, right, what's perpendicular to this one? That's your normal force. I think the person, I couldn't see which person it was, but the person who wrote this down called this the centripetal force. It is true in this case that we would say that the net centripetal force is equal to the normal force because that's the way it points. However, just to be a little bit more complete, we're going to call that normal force going this way, right? So if you've got normal force in this case is what's pulling you in, right? What would I call this force up here then, right? What's keeping me from falling? Anybody got an idea? Now, the reason I'm not falling is because there's friction preventing me from falling, right? Remember, I showed you an example of this before. Let me just turn on my video for a second. So I don't know if you remember when we at the very beginning of talking about friction, right? I talked about if I wanted to hold an object against a wall, right? I could ask you, what force is keeping this up? And you might say it's being kept up because I'm pushing it, I'm applying a force against the wall. However, that's only indirectly true, right? It's very, very indirect, right? My applied force is going into the wall. It's not holding this up, right? It's not holding this book up. My applied force is going into the wall, right? Which is therefore causing there to be a normal force coming out from the wall. And since friction is equal to mu times the normal force, the friction is what's actually holding it up. The friction is the upward force. So in this case, you've got a normal force pulling you in, or sorry, pushing you in the case of the graviton, right? And as a result, you've got friction that's holding you up. Let's see here. question with the book in the wall. Yes. What exactly is a centripetal force? So centripetal force is just a label that we give to the force or combination of forces that are pointing toward the center of the circle, right? So in the case of what I drew just a second ago, right? So I'll go back to this. In the case of this arrow, so the normal force is the centripetal force because it's pointing toward the center is somewhere over here, right? So the normal force is what's pointing towards the center, so we can call it the centripetal force. Is friction always perpendicular to normal force? That's a good question. I haven't thought about it that way, but I think you are right. Yeah, I think it has to be because friction is always parallel to the surface and normal force is always perpendicular to the surface. So yes, Sohaib, I think that that is correct. It is always perpendicular to normal force. All right. Last question. What we got? We got 7 minutes. Okay, good. So here's a question. Now imagine a 900 kilogram car making a right turn. And also remember, a right turn is nothing more than just a quarter of a circle, right? So when you turn in a car, you're just moving at a quarter of a circle. So imagine a 900 kilogram car making a right turn of radius 6.8 meters. What is the force in this case that's pointing to the center? What is the force causing the centripetal force? So see what you can get on that one. Serpentining? What is serpentining?
Serpentining,
What is that?
like in cars. Serpentine,
I don't know what that means.
swerving.
Oh. At our level, it would actually be this. It would be the same instance, but we actually can't address that problem until we talk about rotational motion, which we will do next semester. Because what's happening there is we're treating objects as basically only existing at one point. In order to talk about that, well, you would have a more complicated situation because you'd have your center of mass turning, and then you'd have some rotation about your center of mass. So we'd have to revisit that when we get to rotational motion without having turned before going into the turn. That's the same situation. You just have a higher radius. If you have a gradual turn is just a turn with a bigger radius. What do you mean, no? No, you're wrong. What? Oh, but if you're okay, fair enough. So let me push that question off for a second because there is an answer to that. But let me get through my explanation first, and then I'll that's an interesting question. I'll get to that in a second. All right, what force is causing the centripetal force? Inertia, friction. So yeah, now the thing I want to say about FC, so centripetal force is not necessarily a type of force. It's kind of like a label we give to the forces. So I think many of us are saying friction, and that's the correct answer, right? It's friction that is what's providing our centripetal force. Let me just real quick show you I'm going to go to my document camera for a second because I want to show you a way we might draw a free body diagram for that. So I'm going to imagine, I'm trying to imagine that I've got some perspective here. I'm not an artist, so you're just going to have to bear with me. So imagine you got a car here, right? And this is like a flat plane. and the car is turning like this. So here's the car at a certain point. I want to think about what forces are acting on the car, right? You're going to have gravity, which is going to go straight down. You're going to have normal, which is perpendicular to the ground, so it's going straight up and counteracting gravity. If you say applied, though, right, the applied force is always going to be going forward, because that's the way that your car is trying to go, is forward. So that's not actually providing a centripetal force. The applied force, if you're going at a constant speed, is going to be canceled out by maybe your air drag and maybe some of your friction. And I'm going to call this your friction along the tangent, because it's the friction that's pointing tangent to this quarter turn that you're talking about. What is causing you to turn is this one, right? And I'm going to call this your centripetal friction. So it's a force of friction that's pointing towards the center. That's what's causing you to turn. That's why it's a really bad idea to try and make a very fast, very sharp turn on ice. Because to have a very fast, very sharp turn, you need a lot of centripetal force. The centripetal force is coming from friction. If you're doing this on ice, there's not enough friction to cause you to turn. So just to kind of illustrate this another way, if I were to like look at this same picture from straight down, right? The car is doing this. My normal force would come up out of the page here. My gravity would go into the page. I'd have some applied going this way. I'd have some drag and some friction going this way. But the thing that would be causing me to go in a circle would be this friction, right? So this would be my centripetal force. All right. Before I get to Russell's question, anybody else got any other questions? All right. I'm going to wrap up and let anyone who wants to jump off. And then I'll answer Russell's question. So just there's no homework for today. Just make sure to log in on Thursday. We'll do one more set of notes on Thursday. And then looks like I'll be planning to see you in person on Monday, and we will go from there. So at this point, you are free for the day. So have a good rest of your day. Russell, to your question, so you're imagining, like, I think you're I'm starting by turning slow, turning more and more and more and more and more, right? So the idea is each of these, you can treat each of these as part of a circle. So like at the beginning, you could treat it as a radius, like that's a terrible circle, but a circle of a big radius. And then you can treat this as a circle of a smaller radius. And then you could say if you eventually curve more and more, you could treat this as like a circle of even smaller radius, right? So what you can do, is you can think about this at any individual instant. You can think about it as traveling at a different radius. So you can basically do this calculation at every individual instant, and that would, at each individual instant, it would tell you what the centripetal force is, and then that's how you would approach that situation. Arrows, Thursday is the last day of e-learning. School starts on Friday. Back at school. All right. Anybody else got anything? All right. Oh yeah, go for it.
So last time's work, I couldn't figure out the B part.
Sure. Okay.
Like part B of 10 from last time, and I still have no idea.
All right. Let me pull it up real quick. First of all, let me stop the recording here.